In this video, we're going to introduce the idea of how to calculate the volume of a three-dimensional figure. And the particular three-dimensional figures that we'll be looking at will be formed by taking the area problem that you set up back in section 7.1. And once you've set up the area problem, you're going to revolve that area about some axes. Okay, so if we're looking at the picture that we have shown here on your screen, the original function that they gave you to set up the area problem was just this function right here. So this was our y equals f of x. And our area was the area formed by that particular function. In this case, the x-axis was a boundary, and then the line x equals a and x equals b was also a boundary. So the area problem that you would have set up back in section 7.1 is this purple area here that you see on your screen. And now, to form our three-dimensional object, we're taking that bounded area and we're going to revolve it about this x-axis. Okay, so when you do that, now you see the three-dimensional figure that is on your screen. And back when we did the area problem, when we set up the calculation for our areas, we took a cross-section which was a rectangle. So we took this rectangular slice or a rectangular strip and we calculated the area of one of those, and then we just summed up all of those over the interval from a to b, which was the same thing as taking an integral. Okay, so now if you take that area problem with its rectangular strip and you revolve this rectangular strip around the x-axis, you end up with a new cross-section for our 3D figure that looks like these circular cross-sections. And we refer to these as discs. Okay, so here is one of our cross sections for our three-dimensional figure. And with this being a disc, if we wanted to somehow use the same method as we did with area, where we sum up a whole bunch of these discs, we would just need to know the volume of one cross section, and then we would accumulate those or take an integral of that expression from point A to point B. Okay, well, if we're just looking at a circular cross-section, which is a disc, it's really just a circle with some thickness to it. Right, this right here, from here to here, that would be some sort of thickness. However thick or thin that you would want to make these cross-sections, we could set that up. Okay, and in fact, that thickness we can label as delta x or dx. And really, if you think about it, this is just a cylinder, right? It's just a very flat cylinder. So the volume of a cylinder, that formula is just pi r squared times the height of the cylinder. Well, in this case, the height of our cylinder is just how thick we make each of our cross sections. So the h here we can replace with dx. That's how thick each cross section will be. Okay, now looking at the radius of our disk, if we go in and we draw in our radius, the radius is just measuring from this top function down to the center of our solid. In this case, it's the x-axis. So we are just measuring from y top down to y equals 0, which we could consider that kind of like a y bottom back from our original area problem. Okay, so the radius here is going to be y top minus y bottom. And then that would be squared. And then this pi, well, this pi is just a constant. So now we're going to have this new expression for volume, and we're going to want to sum these. Right? We're going to want to sum all of those up, which is just the same thing as taking an integral. And we're going to integrate from point A out to point B. Okay, and now if you look here in the middle of this page here, we have this formula then, which is kind of our generic setup for each of these figures whenever you're revolving about the x-axis. Okay, so it says that volume is equal to pi times the integral from a to b of our radius squared. Okay, so you just have to identify what is the radius. In this case, it was just y top minus y bottom times dx. And this is if the width of the disk is along the x-axis. So when we look at these cross sections, if you are able to see that you line these up so that they are sitting with the thickness or the height of that particular cylinder or disk is along the x-axis, that makes it a dx problem. Okay, so let's go ahead and look at an example. We are supposed to find the volume of a solid formed by revolving the region bounded by y equals the square root of x, y equals 0, x equals 4, and we're going to revolve that about the x-axis. Okay, so what you're going to want to do is first sketch the area problem to kind of see where your area problem, what that region is, what you're looking at, because from the area problem you're going to set up the volume problem by looking at that cross-sectional piece of the rectangle to get all the information that you need. Okay, so let's go ahead and let's sketch a picture for these. We have y equals the square root of x. So when we sketch that, we're going to have square root of x. We are also bounded by y equals 0, so that is the x-axis. And then we're bounded at the value x equals 4. So our area in question is right here. Okay, and if we go ahead and label this point up here, x is equal to 4, so then y would be equal to 2. Okay, so here is the area problem that we would have set up back in section 7.1. Now, if we look at a cross-section of this area, just like we did in section 7.1 for the area problem, we can see that the width of our rectangle here is dx. And then we're able to see the height here, which would have been the y top minus y bottom for the area problem. Okay, so now if we take this two-dimensional problem and we turn it into the three-dimensional problem, we come over here and we have the same original area that we started with. So x's go from 0 to 4. We still have this point 4, 2. And now we are revolving this about the x-axis. So now we're going to get the bottom half of our solid. Do that a little bit better. We have this new point down here, which is 4, negative 2. And now we can go ahead and show what that solid would look like. Okay, so there's our 3D figure. Now, if we look at that cross-section, what happened there, so the rectangular strip that we had for the area problem, now if we find that cross-section, we now have this disk. Okay, so there's our new cross-section for the 3D. Alright, so now we want to go ahead and set up our problem. We know that the thickness of our cross-sections is dx. We want to know what is the radius of our cross-sections. So I'm going to label that as r. And I'm going to go ahead and write down here that the radius is going to be equal to r of x, and that is going to just be equal to our y top minus y bottom. So y top was the square root of x. I'm running out of room here. I'm going to write this over here. So radius is equal to y top minus y bottom. And from our picture, we see that y top was the square root of x, and y bottom was just 0. So our radius expression will just be the square root of x. Okay, so now for our integral, we're going to go ahead and say that the volume will just be equal to pi times the integral. We are accumulating our disks from 0 up to 4 of the radius, which we said was square root of x, and that's going to be squared because we want pi radius squared, times the height of each of our disks, or the thickness, which is our dx. Okay, so here would be the volume problem. I'm not going to integrate this. You guys are capable of integrating and plugging in then for your answer. Our final answer on this would be 8 pi. Okay, and that would be units cubed for volume. Okay, in the next video then I will show you how to do another example in which we revolve around the y-axis.